For a very long time, humans have imagined what life might be like on other worlds. Thanks to the James Webb Space Telescope, the most powerful telescope in existence, that question can finally be answered. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed some peculiar anomalies from one of the planets in the system, Proxima b. These anomalies, called artificial lights, have puzzled the best minds in the scientific community. But what are they? Do these lights suggest the existence of intelligent life on the planet? Join us as we explore the James Webb's terrifying discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the search for extraterrestrial intelligence, SETI project in 1984. The nonprofit's objective is to gather spaceborne radio signals, as radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. Radio waves are less dispersed or absorbed than other types of radiation, but in the past 30 years, no verifiable alien signal has been discovered. The successful launch of the James Webb Space Telescope has aided in this quest, allowing scientists to examine a range of distant, undiscovered planets orbiting far-off stars. This largest telescope in the world, floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, is pivotal in this research. 20 years ago, there were no known planets outside our solar system, but since then, more than 4,000 exoplanets have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. The Galileo spacecraft turned its equipment back toward Earth when it was en route to Jupiter and found a definitive indication of the presence of plants. The instrument detected the vegetation red edge, VBI signature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth that is covered in a jungle should have a strong and easy-to-detect free signal. The JWST will measure the VBI of far-off Earth-like planets in the habitable zone around stars, which could provide important signs of life in the exoplanet atmosphere. When sunlight crosses a planet's star, the JWST may be able to detect it as it enters the atmosphere. The missing wavelengths would then be discovered via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method may be used to determine the composition of the atmosphere and assess where life is possible. It is likely that life could exist on Earth-like planets with atmospheres similar to our own, predominantly composed of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't usually present, one may be able to detect technological life. Chlorofluorocarbons, CFCs, generated for use in refrigeration and cleaning products, would probably be noticeable to aliens monitoring Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, it would be a clear indication of civilization. However, life on exoplanets might not even remotely resemble life on Earth. Sometimes even earthly life, like extremophile species, can seem alien. This group of organisms, primarily bacteria, can endure environments where other living things would perish. Some can withstand heat up to 250 degrees Fahrenheit, while others can survive in strong acids with pH levels below 3. Given that planets like Earth are more likely to support life than planets with severe temperatures or acidic conditions, it could be a good idea to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star, which is less common and typically has shorter lifespans in our universe. The likelihood of studying planets orbiting around red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. These stars have significantly longer lifespans, allowing more time for the formation of life and evolution to produce complex life forms. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of which may have liquid water on their surfaces. Despite having a much smaller and colder mass than our Sun, the TRAPPIST-1 star radiates light that is similar to that of Earth due to the close orbit of its planets. The best chance for humans to see city lights outside the solar system lies with Proxima Centauri. A red dwarf star that is 4.25 light-years from the Sun. Proxima is about 600 times fainter than the Sun. So a planet must be 20 times closer to it than Earth is to the Sun in order to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, situated in a Goldilocks zone where the light intensity is just right to melt water. Proxima b circles Proxima Centauri. It's possible that Proxima b is an airless, lifeless planet, given that it orbits its red dwarf star at a distance of only 46 million miles, compared to the 93 million kilometers between the Sun and Earth. The planet is in a close orbit that exposes it to strong solar winds, which can completely destroy its atmosphere. However, it also receives enough sunlight for temperatures and liquid water that are similar to those on Earth. Proxima b is thought to be tidally locked, always showing the same side to the star, much like the Moon does in relation to Earth. Proxima Centauri is about 18% the mass of the Sun and burns far less brightly than one might anticipate for a planet so near to its star, just 5% of the Earth-Sun distance. One might expect it to be a red-hot tinderbox, but liquid water could easily exist on Proxima b as long as the planet has an atmosphere to hold heat in. Since the total energy reaching it from the Sun is only 65% of what Earth receives, the planet is not especially friendly to life. It is most likely tidally locked, which means that it always faces the same direction toward the star, producing permanent day and night sides with significant temperature changes. The planet also receives 100 times as much high-energy radiation as Earth does because of its proximity to Proxima Centauri, including X-rays and ultraviolet light. Proxima b is bombarded with high-energy particles during star flare-ups. Unless it has a shielding magnetic field similar to Earth's, the conditions for life could be extremely harsh. However, there are certain realistic conditions that could make it a more pleasant world. Models suggest that the atmosphere of tidally locked planets may be susceptible to a rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, the atmosphere is less likely to escape. Given that we don't know anything about Proxima b's volcanic activity or magnetic field strength, we can't even guess whether or not the planet has an atmosphere. However, since an atmosphere presupposes the existence of seas, and the two taken together presuppose the existence of life, we are desperate to know if Proxima b harbors a sophisticated civilization. It might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima b has triggered a race to determine if it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, enabling them to calculate its density. Knowing the density would validate the planet's rocky makeup and provide information on the materials used to create those rocks. During a transit, starlight might pass through the planet's atmosphere, potentially disclosing its nature. However, the likelihood that the orbit will be in the right alignment for scientists to observe a transit is merely 1.5%. Additionally, the star's propensity to flare complicates matters. Astronomer David Kipping of Columbia University states that the star's heat causes a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. The James Webb Space Telescope was created specifically to study infrared light, and Proxima b's infrared heat signature is key to identifying the planet's atmosphere. The infrared portion of the spectrum has a strong affinity for Hubble's successor. The JWST will be able to observe city lights on Proxima b's night side, even if they were as faint as what our civilization currently employs on Earth's night side. The JWST could detect artificial illumination as long as it was constrained to a frequency band that is 1,000 times narrower than the starlight. Proxima b's day side is heavily covered with solar panels. Because of its unique spectral edges, it is able to reflect starlight. As Proxima b revolves around its star, day and night are identical, with cool evening lows following daytime highs. The difference in temperature between day and night, however, depends on whether or not the planet is entirely composed of bare rock. An atmosphere and ocean both conduct heat. In other words, if there is an atmosphere, Proxima B's dayside and nightside temperatures will differ more. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, it will only take the JWST 112 Earth days to measure the radiation from Proxima B's two faces after it has successfully completed its orbit around the star. In the event that Proxima B has an atmosphere, the next step will be to analyze its makeup. The presence of gases like oxygen, water vapor, and methane in particular could indicate the existence of habitable circumstances, if not actual living things. To accomplish this, we must successfully capture starlight as it bounces off or travels through the planet's atmosphere, which is a very difficult task. However, the JWST can only closely examine a few of the closest potentially habitable worlds because it was not built to look for extraterrestrial life. Additionally, it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. The JWST is unable to detect the presence of unbonded oxygen, which is the strongest sign of life. Even if some mixtures of these gases may be suggestive of life, one of the planned ground-based observatories that will be able to conduct a thorough atmospheric investigation is the extremely large telescope, which is scheduled to begin operation in the middle of the 2020s. Ozone may be among the substances that the JWST is capable of detecting. Until those telescopes are operational, the JWST may provide information that we can consider for a decade into the future. Even more powerful space telescopes may employ cutting-edge techniques to conceal the blinding brilliance of a planet's host star and reveal starlight reflected back from the planet. This process could be akin to covering the lights with your hand to improve your ability to see distant objects. Future space telescopes might achieve this by using small internal masks or large, outside umbrella-shaped satellites. After starlight is blocked, studying light reflecting off a planet is much easier. Unfortunately, the majority of gases produced by terrestrial life can also be produced by non-biological factors. Methane, for instance, is a gas that both cows and volcanoes release. Sunlight does this as well, converting water molecules into oxygen and hydrogen through photosynthesis. When searching for alien life, astronomers are sure to come across some false positives. They must have a thorough understanding of a planet of interest to assess if its geologic or atmospheric processes potentially resemble a biosignature and help rule out false positives. The next wave of exoplanet research may produce the compelling evidence required to establish the reality of life. The James Webb Space Telescope's preliminary data gives us a preview of the significant advancements to come. If there is life elsewhere in the cosmos, it is one of science's most pressing questions. It's possible that life is abundant throughout the cosmos, or it's also possible that we are completely alone and trapped on a solitary planet in deep space. In either scenario, significant philosophical and psychological adjustments among people will likely be necessary for the eventual resolution. The quest to discover life beyond Earth continues to drive scientific innovation and exploration. With each advancement in technology, our understanding of the universe expands, revealing more about the potential for habitable worlds. Beyond the intriguing findings related to Proxima b, other exoplanets have also garnered attention. For instance, the Kepler Space Telescope has identified numerous Earth-like planets in various star systems, some located in the habitable zone of their respective stars. These discoveries prompt scientists to rethink the conditions necessary for life. Researchers are increasingly considering alternative biochemistries, such as those based on silicon instead of carbon. Such possibilities widen the scope of potential life forms that might exist under different environmental conditions, including extreme temperatures or high radiation levels. Moreover, astrobiology has become an interdisciplinary field, combining insights from biology, chemistry, geology, and astronomy. This collaboration allows for more comprehensive models of what life could look like elsewhere. For example, studies of extreme environments on Earth, like hydrothermal vents and acidic lakes, have led scientists to hypothesize about similar ecosystems existing on other planets or moons, such as Europa or Enceladus, where subsurface oceans may harbor life. Future missions, including the European Space Agency's Ariel and NASA's upcoming missions to Mars, will further investigate atmospheres and surface conditions of these distant worlds. Mars, in particular, remains a prime candidate for finding signs of past or present life, as rovers like Perseverance continue to search for organic compounds and study the planet's geology.